What's up? Hey, everybody. Welcome back. So we've got some exciting new things in this video. We are going to introduce a major concept in mathematics beyond just Calc2. And this is the idea of a power series. So much of our work with series so far has been building towards this new idea of a power series. So my goal in this video is to introduce what a power series is, and talk about a idea in which a power series converges. And with power series, this means talking about a radius of convergence and an interval of convergence. And we will end the video by working through one or two quick examples to sort of illustrate these concepts more concretely. Okay, so first of all, what is a power series? Well, a power series is formally, it is a series that has a variable x in it in a sort of prescribed way. So a power series, we're going to set it up to look like a function. We'll define what it means to be a power series centered at a point x equals a. And it is simply an infinite series of this form right here, right? So it's our series notation that we know and love. Sum as n goes from 0 to infinity of some coefficient c sub n times x minus a raised to the nth power. And now notice, as we begin to list some of these terms, they look like this. So for the first term, here, let me get the spotlight. For the first term here, we just have c sub 0 times x minus a to the 0th power. So it's just c sub 0 plus c sub 1 times x minus a raised to the first power, plus c sub 2 times x minus a raised to the second power, plus c sub 3 times x minus a raised to the third power, and so on and so on and so on. So notice a partial sum in this power series, right? Like if I just took these first three terms that are visible here, right? That kind of looks like a polynomial, a second degree polynomial, right? In which we have an x squared term, an x term, and a constant term. And so a power series is going to be sort of formally this expression that kind of looks like an infinite polynomial. Of course, that's a little vague and a little hand wavy because infinite polynomial isn't really a well-defined concept. I want to highlight that this really is a function in the sense that it does take real numbers as input values, right? So plugging in a value like an x, and the output is a real number, assuming that the associated series converges, right? So for example, let's say I went ahead and I plugged in the value, like you plug in an x value. Let's say I plugged in the value x equals 5. Why not? Right? Well, I'm plugging in an input, and my output will be potentially a number as well, right? So we would get c sub 0 plus c1 times 5 minus a plus c2 times 5 minus a squared plus so on and so on. It would really be an expression that looks like this, right? And assuming that a is a constant, and these c's, right, are themselves constant. So c sub 0 is a number, c sub 1 is a number, c sub 2 is a number, and so on, right? What I have here is nothing more than a series. And so we now have experience with series. We know that sometimes they converge to a number, sometimes they diverge. And so what we really have here is a function where you input a number and you output a series which might converge to a number itself. And so as long as our series converges, then this is a function where you input a number and the output is whatever number that series converges to. Okay, so how do we determine, and maybe I should say this is the big question when it comes to these power series, how do we know whether a power series converges or diverges at a given value of x? Well, it turns out that all of these series tests that we've been developing along the way will be extremely, extremely helpful, extremely useful for determining whether or not these series converge or diverge. And we'll see a little bit of that in a moment. However, I want to introduce here this very interesting idea that we discover as we look at series convergence and power series convergence. And that is specifically if our power series is centered at a given value, right, like at x equals a, then the numbers at which our series converge will form an interval around that number a. So when we talk about a power series centered at a, this is really what we mean, right? That our series will converge definitely at a, and it will converge for some interval centered at a, right? And so if we consider the values at which our series converges, it will converge at a, and it will converge for some interval of radius capital R. So there is this value capital R, the radius of convergence, that helps us determine where and for which x values our series converges. And it turns out there are 3 possible cases. Case number 1, our series only converges at x equals a, and the radius of convergence is equal to 0. Notice our series will always converge at least at x equals a, right? Because if I plug in x equals a, then my series will take the following, right? My series will just take the form c sub 0 plus c sub 1 times 0 plus c sub 2 times 0 plus c sub 3 times 0, and so on and so on. In other words, I'll cut back one slide. If I plug in x equals a, right? So maybe not 5 this time, but if I plug in a, I'm going to get this expression here, in which every term except for the first term is just going to be a 0, right? This term will be 0, this term will be 0, and so on and so on. And so that whole thing converges to c sub 0. So our series definitely converges in the case where x is equal to a. And in case number 1 here, there it is. In case number 1, that is the only point where our series converges. Every other x value causes the series to diverge. So case number 1, f of x only converges at this one point, and the radius of convergence is equal to 0. Case number 2, f of x converges no matter what x value I plug in. I can plug in any x value, and the resulting series is a convergent series. In that case, we say the radius of convergence is equal to infinity. The third case, and maybe most interesting case, is what happens when our interval of convergence is some positive r value that is less than infinity. Right? So the third case says that there is some number r such that f of x converges absolutely if we are within a distance r of the center point a, and diverges if we are outside of that value, if we're distance greater than r, and then it may or may not converge at the endpoints. So in this case, we have a value a, we have a finite radius of convergence r, so we go out r distance in each direction, and then within this interval, our series converges absolutely, while outside the interval, our series diverges. At the 2 endpoints, our series may or may not converge. We would have to examine each endpoint separately. And so this gives us different kinds of intervals of convergence depending on which case we're in, right? So in the first case, f of x converges only at x equals a. We have an interval of convergence that is just the point a by itself. So I could write that as the set containing the point a, or I could write it as the closed interval from a to itself, right? But it's an interval of convergence that consists of a single point. If f of x converges for all x values, then our interval of convergence goes from negative infinity all the way up to infinity. Any one of those x values would be fine. In this third example, right, the sort of the core interval of convergence, or the interval of x values on which our series converges, is going to be the interval from a minus r up to a plus r. Right, so that's sort of a way to denote in interval notation this idea of starting or centering our interval at a, and then going out plus r to minus r, going out that far in each direction. So that could be our interval of convergence. However, we would have to check the endpoints, right? The interval may or the series may or may not converge at these endpoints. So other possible intervals of convergence include the one in which we include the left endpoint, but not the right endpoint, which we include the right endpoint, but not the left endpoint, and the one in which we include both endpoints. So we end up with something that kind of looks like this. So these are the four possibilities, or I should say, I'm sorry, these are the three possibilities for radius of convergence and the associated intervals of convergence that happen. So these are the different kinds of intervals on which a power series might converge. Okay, let's look at an explicit example and try to find the radius of convergence and the interval of convergence for this lovely power series. The series then goes from 0 to infinity of x to the n. Notice, this is written in the form the sum n equals 0 to infinity of c sub n times x minus a to the n. It just so happens that all of our c sub n's are equal to 1, and a is equal to 0. So this is an power series that is centered around a equals 0, and all of our c sub n's, all of those coefficients, are equal to 1. So let's try to figure out what the radius and interval of convergence are for this series. And it turns out this series is nothing more than, notice the series, if we were to spell out the first few terms, it's 1 plus x squared plus x cubed plus dot, 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 right? This is a geometric series with a constant ratio of x, right? It's geometric because as I go from one term to the next, I have this common ratio, and the common ratio in this case just so happens to be x, right? So I multiply by x to get there, and then I multiply by x to get from x to x squared, and then I multiply by x again, and so on and so on. And so we know something about geometric series, right? Since this is geometric, it converges if our common ratio, r, which in this case is just the value x, is less than 1. This converges if x is less than 1. Right? Specifically, if absolute value of x is less than 1. And so we actually get here that the radius of, and I should say it diverges, right? Diverges if x is bigger than or equal to 1, right? And so what we have here now is a radius of convergence and an interval of convergence for this series, right? We can say that, and I'll usually use this notation, the radius of convergence, ROC, is capital R equals 1, and the interval of convergence, the IOC, is from -1 to 1. So if I plug in any x value in between -1 and 1, we will get that this power series is well defined. Furthermore, I can say one thing further, and then I'll pause. So I can say that for geometric series, I actually know what my series converges to, right? And so we actually get this kind of powerful observation that for all x values between -1 and 1, the sum, as n goes from 0 to infinity, of x to the n, when thought of as a function, well, that just converges to 1 over 1 minus our r value, or in this case, 1 over 1 minus x. So not only can I think of this infinite power series as a function, but in the case of a geometric series, I have a nice explicit formula that tells me what it is. Okay. Okay, I want to work through one more example reasonably quickly. I know this video is starting to get a little long, but one more fun example. Let's take a look at this power series to determine, and we'll use the ratio test to determine at least the radius of convergence. So we might not get a nice formula for this power series. We might not explicitly determine the interval of convergence, but let's see how we can use the ratio test to help us out here. Okay, so here is our power series, right? The sum as n goes from 1 to infinity of x raised to the 2n divided by 2n factorial. That will be our power series f of x. To determine if this converges, we want to use the ratio test, which says that we create a ratio of the nth term, so that's x to the 2n over 2n factorial, divided by, and then not divided by, that's in the denominator, so we will divide the n plus 1th term by that. So this becomes x to the 2n plus 1 divided by 2n plus 1 factorial. Right, so that's the n plus 1th term in the numerator, that's up here. We have the nth term in the denominator, that's down there. And then we would take the absolute value of this ratio and then take the limit as n goes to infinity. And the question is, for what x values is this limit less than 1? Because the ratio test required that we had our limit be less than 1. So let's take a look at this. We can rewrite this and simplify it a little bit. So I'll still have these giant absolute value signs, but this can become an x to the 2n plus 1 divided by an x to the 2n times, over here we can get 2n plus 1 factorial under 2n factorial. Right, so that's now the quantity that we're trying to take a limit of. We do that, we're going to get x, let's think, so 2 to the n, x to the 2n plus 2 divided by x to the 2n, we're going to get an x squared times, and here we're going to get 1 over 2n plus 1 times 2n plus 2, right? Because the lower terms in the factorial will cancel each other out. And so this, right, is going to be the object that we take a limit of as n goes to infinity. All right, and what we see is that for any fixed x value, so here's an important part. We want to think about a fixed x value. And for a fixed x value, this just becomes a fixed number squared times a fraction where the denominator is getting bigger and bigger and bigger. And so this will end up going to 0 for any x value. And the end result is that this series will actually converge no matter what x value we use. For any x value that I look at, this series converges by the ratio test because that corresponding limit equals 0. So the end result is that our radius of convergence is equal to the entire real line from negative infinity. Whoops, I'm sorry. The radius of convergence is equal to infinity. And the interval of convergence is going to be from negative infinity to infinity. Okay, great. That's all we got for this video. I will see you all next time.